So let's take a look at an example problem now from our text. So we're going to take a look at example problem 10.3.1. This is going to have to deal with the effect of gain on modeling approximation. So for a system that we see here down in the figure below, they tell us that the plant time constant is given to us as 2. And the nominal value of the actuator time constant is given to us as tau sub a is equal to 0.02. They ask us to investigate or look at the effects of neglecting this time constant as our gain, given to us as k sub p, is increased here. So we can see over here we have our r sub s coming in. Here's our k sub p right there, our gain right there. Going in, we have this function over here, 1 over our tau as plus 1, where they're telling us neglecting this time constant, what are the effects of it, neglecting the time constant there. And this goes into our function here of 1 over 2s plus 1 to our cs over here. So again, effects of neglecting our actuator time constant is what we're looking at within this problem. So now that we've had the opportunity to read through the problem statement, understand what they've given to us and what they're asking us to solve for, now what we can do is go ahead and create our setup page here. So on our setup page, we have the course number, example problem number that we're working on. This is effective gain on modeling approximation. So what are our given values from our problem statement initial diagram? Well, they tell us our tau sub a, our actuator time constant here, is equal to 0.02. They're telling us our Kp is going to be increased and that our plant time constant is given to us as 2, and we can see that right down here in our block diagram. So our block diagram, we have our input r sub s coming in over here. We have our c sub s over here coming out there, and then we have our k sub p gain right here, and then we have these two functions right there. So we have 1 over tau a s plus 1 and 1 over 2s plus 1 right there, where our tau sub a is what we're going to plug in as our 0.02, but also we're going to plug this in as 0. So we're going to solve it with two different values for tau sub a, and this is in order to see what happens when we neglect the effects of the actuator time and the constant, so 0 versus our given value of 0.02 when we solve this out. So what I do now is I begin my solutions. I redraw out our block diagram here, and I add in a couple other little variable names just to help us as we're setting up our equations for our solution. I add in our E sub s and our B sub s, our feedback, and our AR right here. So as I plug those into this equation, now what I can do is I can come up with 3 governing equations for this block diagram for our feedback here. So I have my C sub s, and my C sub s is right over here. I'll say, okay, what comprises that? Well, I have my K sub P times my function here, 1 over tau a s plus 1, times my function here of 1 over 2s plus 1 plus this e of s right there. So that comprises equation number 1 here. Now what comprises e of s here? Well, we have our b of s coming up into this and our r of s coming into it. So it is a r of s minus b of s gives us our e of s function right there. And now we can see that our b of s, because we have nothing in our feedback loop here, there's nothing there. So therefore, this is simply equal to c of s. So now I have 3 governing equations here, 1, 2, and 3, that we can reference back to. What we want to do now is eliminate the extra variables within this. So we can say, okay, here's our governing equation from equation 1. There's c of s is equal to, and I multiply my k sub p through right here. I'm going to leave it in terms of tau sub a as I start right now. This is k sub p over my tau sub a s plus 1 times 1 over 2s plus 1 times our e of s there, where from equation 2 now we have something we can plug in here for our e sub s. So e sub s is equal to our input r sub s minus our b sub s from our feedback loop there. So we can plug that all in right here. So we plug it in, we end up with is our c sub s is equal to k sub p over tau a s plus 1 times 1 over 2s plus 1 times our e of s right there. Again, now we plug this into our e of s right there from equation 2. So we end up with this equation here. We plug in. This is now rs minus b of s right there. But we also now know that we have a relationship for b of s from equation number 3 right here. So b of s is equal to c of s here. So we can plug that right in to our equation number 1 for c of s there. And when we plug in that equation C, our relationship between B of S and C of S, we end up with this relationship here. The C of S is equal to Kp over our tau A S plus 1 times 1 over 2S plus 1 times Rs minus Cs. Now, what we can see is we have a Cs on this side and a Cs on that side. So we need to get Cs on its own. So we need to do a little bit of manipulation, simplification of this equation in order to get C of S on its own. So the first thing I do is I distribute through here with this equation. here, so I can combine this and this. So I combine these two together. What I end up with here is a k sub p over tau as plus 1 times 2s plus 1 when I combine these two equations together. Then I distribute that through my r of s and my c of s there. So I end up with r of s times kp over tau as plus 1 times 2s plus 1 minus now the same thing times my c of s right there. So that's just distributing that through. So now I can look at this and say, okay, I got a C of S there and a C of S there. Let's get our C of S both on the same side. So I can add this whole right side of the equation right here to both sides of the problem. When I do that, I end up with C of S plus C of S times my K sub P over tau A S plus 1 times S2 plus 1 here is equal to, now my right-hand side of the equation, just my RS times that same thing here, my K sub P divided by tau A S plus 1 times 2S plus 1 right there. So what I realize here is right here I can pull out a C of S. So I pull that out, and C of S times 1 for that guy right there, plus now my K sub P over my tau A S plus 1 times 2S plus 1 there is equal to, my right-hand side doesn't change at all. That stays the same there. So from this point now that I have this relationship here, and I do have C sub S on the side, on one side on its own, I want to get it completely alone. So I'm going to divide through by my R of S on each side here. So I have now my C of S over R of S right there times this relationship, my 1 plus K sub P over tau A S plus 1 times 2S plus 1 there is equal to K sub P times K sub P over my tau AS plus 1 times 2S plus 1 right there. So the next thing that I can do now to try to get my C of S and R of S by themselves over there in the form that I'm used to is divide through by this 1 plus K sub P over my tau AS plus 1 times 2S plus 1 on both sides. So I do that there and I move it over. I end up with this relationship right here now for my C of S over my R of S. So I left this in general form. I could have started foiling these out. I could have put in my values for TA, but I wanted to leave it in general form right now, even though it is a little bit longer and more involved. And now from that, though, what I can do is plug in for any tau sub to A or whatever value I need to sub in here. So I do that now for the part where I'm ignoring my time constant here. So if I'm ignoring it, I'm saying that tau sub A is equal to 0. So everywhere there's a tau sub A in this, I can plug in a 0 here and end up with this new relationship right here. So reduce that down. I have now my C of S over my R of S is equal to K sub P over 2S plus 1, all over 1 plus K sub P over 2S plus 1 right there. So now in order to find my roots, what I can do is I can set my denominator equal to 0, find the roots. I do that there, set my denominator equal to 0. 0 is equal to 1 plus K sub P over my 2S plus 1. Well, let's move things around, solve this thing here for S. So what I want to do to solve it for S is I can subtract a 1 there and subtract a 1 here. What I end up with now is negative 1 is equal to K sub P over 2S plus 1. So the next thing I want to do is multiply both sides by 2S plus 1. Multiply them both by 2S plus 1. I end up with negative 2S plus 1 is equal to my K sub P. Can add a 1 to both sides of this here. So 2S is equal to KP plus 1. Let's divide through by 2 on each side here. So I have that negative S is equal to KP plus 1. All divided by 2, or I can rearrange that and get rid of the negative sign from the S and end up with this relationship right here for S. So now that I've gone through and solved this for S for my T sub A is equal to 0, so I'm ignoring my time constant they asked me to do, I want to go back through and resolve it again, and this time for the time constant T sub A that they give us in the problem statement of 0.02. Now, I solved the whole first part of the problem in terms of variables and terms of my tau A, so therefore that saves me a little bit of time now, and I can go back in and plug in for my tau A here for whatever value I need. But as I go through, the first thing I'm going to do is leave it in terms of tau sub A as I reduce and simplify, and then at the end, I'll plug in for my value of 0.02. So the first thing I need to do in order to get my roots is set my denominator of this guy equal to 0. So I can set this guy right here, my denominator of this, equal to 0 here. So 0 is equal to 1 plus now this whole value here of K sub P divided by my tau A S plus 1 times 2S plus 1 there. So I'm going to move my 1 over the other side by subtracting negative 1 from both sides of my equation here. I end up with negative 1 is equal to my K sub P over my tau AS plus 1 times 2S plus 1 here. So now what I realize, I'm going to take and multiply through by my denominator here, move over to the other side. So I have -1 times my tau AS plus 1 times my 2s plus 1 here is equal to k sub p. And then I'm going to take and FOIL these guys out to simplify it down. So I have -1 times, when I FOIL this all out, first outside, inside, last, when I multiply through this guy here, I have tau AS squared plus tau AS plus 2s plus 1 is now equal to my kp. Well, let's get our 1 over to the other side here. So we're going to move that over to the other side by dividing by a -1 on both sides of our equation there. And we end up with tau AS squared plus tau AS plus my 2s plus 1 is now equal to -kp. So I'm going to move my kp, my -kp over here and set the whole thing equal to 0. So I end up with this relationship here. We have tau AS squared plus tau AS plus 2s plus 1 plus kp is equal to 0. Now we can solve this equation multiple different ways in order to get our s value. So one way that we can do this here now is, first thing we want to do is plug in for our values for our tau A. So this is just in terms of our variable s here, so we can solve for it. So we're given the fact that our tau A is equal to 0.02. So we can plug this in now. Everywhere there's a tau A, my 0.02. Plug this in. When I simplify this down, I end up with 0.04 s squared plus my 2.02s plus 1 plus kp is equal to 0. Solve this for s. I can get it in terms of this relationship here. For s is equal to -50.05 plus or minus the square root of 2,450.25 minus 100 kp. So as our kp increases, we can plug those in. We can do that in a numerical solver, a t-chart from there, in order to get exact values for s as our kp value increases.